All right. So I wanted to resume some reading. It's been a couple days since I have been working, actually quite a few days since I got a reading done on this book. So wanted to get at least a couple hours in today, this afternoon, to make some progress on the reading, because it's quite a lot of reading that I need to do here. Ugh. I actually threw the book on the ground over here because I had other things I had to focus on. Alright, let me pull my light over here. That seems like really intense. Maybe I'll do top down light? No. Let me see if I can turn the light on in the room here. See if that'll be... Yeah, that's good. I lost my pen too. Let me grab that pen and my highlighter. Alright. So, I clearly left off on this page, but I don't even remember what he was talking about. So maybe we go back one section to the previous page and we will resume. Wait a minute, that doesn't seem like the previous page. Something's wrong there. The program counter, we talked about all that, yeah. Okay, maybe we were here. Alright. I think I'm going to stop at this aside. Ever-changing forms of generated code. Let's go back to maybe this section here and resume from there. I had some highlights in this section, so I know I read it, but I just want to kind of get some context on what we're reading. So whereas C provides a model in which objects of different data types can be declared and allocated in memory, machine code views the memory simply as a large byte addressable array. Aggregate data types in C, such as arrays and structures, are represented in machine code as contiguous collections of bytes. Even for scalar data types, assembly code makes no distinction between signed or unsigned integers, between different types of pointers, or even between pointers and integers. The program memory contains the executable machine code for a program, some information required by the operating system, a runtime stack for managing procedure calls. Let's start from the beginning of the paragraph, because it's going a little too fast here. The program memory contains the executable machine code for the program, so that's going to be like your text section. Some information required by the operating system, a runtime stack for managing procedure calls and returns, a block of memory allocated by the user, e.g. using malloc library function. As mentioned earlier, the program memory is addressed via using virtual addresses. At any given time, only limited subranges of virtual addresses are considered valid. For example, x86-64 virtual addresses are represented by 64-bit words. In current implementation of these machines, the upper 16 bits must be set to 0, so that's 48 bits available for addresses. And so an address can potentially specify a byte over a range of 2 to the power of 48 or 64 terabytes. More typical programs will only have access to a few megabytes or perhaps several gigabytes. The operating system manages this virtual address space, translating virtual addresses into physical addresses of values in the actual processor memory. Yeah, it manages it, but the MMU and TLB kind of take care of the mechanics of it. A single machine instruction performs only a very elementary operation. For example, it might add 2 numbers stored in registers, transfer data between memory and register, or conditionally branch to a new instruction address. The compiler must generate sequences of such instructions to implement programmed constructs such as arithmetic expression evaluation loops or procedure calls and returns. So the side up here says, in our presentation, we will show the code generated by a particular version of GCC with a particular setting of the command line options. If you compile code in your own machine, chances are you will use a different compiler or a different version of GCC, and hence will generate different code. The open source community supports GCC, keeps changing the code generator, attempting to generate more efficient code according to code changing guidelines provided by the microprocessor manufacturers. Our goal in studying these examples shown in our presentation is to demonstrate how to examine assembly code and map it back to constructs found in higher level programming languages. You will need to adapt these techniques to the style of code generated by a particular compiler. Code examples: suppose you write the C code mstore. So I remember writing this, or copying it, I should say, from the book's text. Mstore, please. Thank you. Different? Slightly different. Not very different. Yeah, okay. We'll do get at all, just start tracking things. To see the assembly code generated by the C compiler, we use the -s option on the command line. So we say, hey, because I did it on all different types of compilers to see their output. Makes sense. This will cause GCC to run the compiler, generating the assembly file mstore.s and go no further. Normally, it would then invoke the assembler to generate the object code file. The assembly code file contains various declarations, including the following set of lines. So we were opening up this thing. No. Vim. The GCC thing. I think it was a. Well, let's do our make here, just to make sure everything's good. Build. I just want to see in here vim clang.s. Something's wrong there. We'll just say clang hey. So clang has a bunch of metadata. The mstore return quad word has some comments in here, and then some like end function thing with some address signatures. Lots of metadata. That's what all these dot things are. So all this is like metadata. This is all metadata. That's metadata. These are comments. This is metadata, right? Yeah. More metadata. So this would be the actual instructions. And if we compare that to GCC, okay, it's not going to allow me to do that. mstore.gcc. Let's do the same process, delete all the metadata. It looks almost identical. In fact, I think it is exactly identical. Write quad word instead of write q. Actually, no, I'm going to do that to all these. Vim, mstore, because they're build artifacts, I can rebuild them. So if we delete everything here, and of course, delete that. What is this temp thing? Interesting. Lots of more junk on the Zig side. And then if we do delta between GCC, mstore.gcc and mstore.clang, it seems that clang is using the quad word, preferences quad word instead of 32-bit. And then if we do with Zig, it's going to be totally different. Zig. Yeah, it's just totally different. Uses different registers. Totally different. So an observation. I'll just add it to the make file here. Looking at the generated.s files, Zig CC generates way more instructions and uses different registers. then cling and cling. And then if I do Shift V, GQ, no, GC, sorry. There we go. And then select GW. I don't know why it's GW on this Vim, but we'll go ahead and add that. Cool. So now we're going to go into, I guess, this code example section. Suppose we write a C code file mstore containing the following function definitions. So we have our mult2 long mult store. To see the assembly code generated by the C compiler, you can use the -s option on the command line. This will cause GCC to run the compiler generating the assembly file mstore.s and go no further. Normally it would then invoke the assembler to generate an object code file. The assembly code file contains various declarations, including the following set of lines: mult store push q. So let's go ahead and I'm going to go ahead and make it again. Make clean make vim build mstore.gcc, just so that we can follow along here. So push quad word, yeah, it does that. So if you look at the code in the book, the first one is push quad word of the base pointer. So we're just saying save off the base pointer, and then we're going to move our dx into the base pointer register. So we're resetting the base pointer to wherever our dx is. And I thought our dx would be the stack pointer. I've seen that before. MD64 register table. RBX. I thought RSP would be the stack pointer. RBX, sorry, this is base pointer. DX, which is a third integer argument. If we look at the code again, okay, it's a destination. Interesting. So we have two functions here. This call here is not actually in the object file, so it just forward declared, so we're just say, hey, call that at some point. So again, push the base pointer onto the stack and then set it to dx, which is a third integer argument, which I assume. Is this right to left? I always get confused. So this looks like AT&T syntax. Let's ask AI real quick. Oh, this is the website that we didn't do yet. I'm just gonna close that out for now. I just don't want to be distracted by it. If we open up here and go to README, there is a website here, and it's called, let's go back, 1, 2, 3, 4, 5, 6, ASM I32. I32. We'll just leave that there. Okay. Kill that. Okay. What syntax of ASM is this? I think it's Bell Labs AT&T syntax, and I think it is assignment is right to left. And what order are the operands? Ooh, I'm sneezing my ass off this morning. Ah, I think I have like dry nose or something. It's getting dry here in Colorado. AT&T syntax. Yep. Percent sign is the easy way to identify AT&T. Immediate start with dollar. No immediate values here. Instruction suffixes indicate operand size. Okay. Memory uses are in parentheses instead of brackets. Operand order is source and destination. So AT&T is assignment to the right. Okay. So let's try to decipher this ourselves. So we're going to move quad word. So we have the RDX register, and we're going to say whatever's in RDX, we're going to put into RBX, which is the base pointer, which is odd that that is there. And then we're going to call to mult2 at PLT. So basically, like, we were called with long destination, and it just wants long. It doesn't need destination. Our dx is the third integer argument, so we store that at base pointer. Oh, so we're saying like this is going to be the return. When we call that thing, it's going to write into the address here, I think. No. Our AX is the return value. We store it into whatever RBX points to. I guess I don't understand why they used RBX here. Pop quad word into RBX and then return. Let's go back to AI and see if it had an explanation for this that matched what I was thinking. Did I get the whole thing? I forget. No. We'll go up here and we'll say, explain this ASM output line by line. Assembly directives starting with dot, labels, actual instructions, dwarf, call frame, info. CFI is call frame info. Source destination. Say move RX into RBX means move RAX into RBX, yeah. File setup. Section assembly director telling debugger the source file name. Used for dwarf debugging, stack traces source mapping, no runtime effect, text. Switch assembler into text section. Okay. This section holds executable code, equivalent to saying section text. Global mult store exports a symbol so that it's visible to the linker, meaning mult store is externally visible. Without this, the function would be local to the object file. Mult store at function. Tells elf symbol table that mult store is a function symbol. Helps tools like objdump, gdb, and readelf. Function entry. Mult store, the label marking that, linker will make use of this address of the function. This stuff, I'm kind of curious what that is. LFB0, local label used for debugging metadata. LFB is label function begin, label function end. Okay. GCC uses these to delimit function boundaries. Okay. I've always just seen like, okay, this is the label for the function, but you have these begin and ends, which I guess the debugger uses. Call function, what is this thing called again? What is it called? Call frame information. Start of call frame information for unwinding, used by debuggers, stack unwinding exceptions, backtraces, no effect on execution. Call frame information, okay. So we're saying start of the proc, call frame something offset, another offset, another offset, and then nproc. Okay, function prolog, which is to push quad word of RBX onto the stack, which goes into the instruction subtract 8 off of RSP and write RBX into RSP. Why? Because RBX is a callee saved register in the systemv ABI. I thought RBX was the base. Oh no, RBP, not RBX. Okay. So what is being passed here? RBX. I don't even know. Callee save register. This is the API. If the function wants to use RBX, it must restore it before returning. Okay, we're using this for storing the return value, it seems. Okay. CFI def CFA offset 16, CFI metadata, canonical frame address. So call frame information, canonical frame address, meaning stack frame size is equal to 16 bytes. So the whole frame is 16 bytes. I guess that could be determined statically that you only ever need 16 bytes. Used for stack unwinding. CFI offset 3, negative 16. More unwinding metadata, registered numbers follow dwarf numbering. 3 is RBX. So it's saying where RBX is stored, which would be negative 16 from the base, which is RBP, not RBX. I was confused there. So I wonder why it's not doing the whole thing where in the prologue where it saves off the base pointer and updates it. Meaning saved RBX located at CFA minus 16. Okay, saving a function argument. Move quad word of DX into RBX. So DX is a destination, it was a third integer argument. Why? Because the function needs to preserve the third argument across a function call. Okay. We're going to call into a function we don't want to get destroyed. So we save it off into RBX. When calling a function will not be changed according to the calling convention. This is a really helpful table here. I'm going to bookmark that. RDI, RSI, RDX, RCX, R8, and R9. RDX holds the third argument. Since the function calls another function mult2, and RDX is caller saved, GCC copies it to RBX, which is callee saved. Okay. Function call. We have a call to mult2, calls another function. Procedural link table is used for dynamic linking. I guess you can resolve that statically, right? I don't see why you can't. Call flow, call PLT stub, dynamic linker, actual mult2. I think you can do it statically though. I don't think it has to be dynamic. Register is used for arguments remain unchanged unless modified. Return value comes back as RAX. Yep. And then we store RAX into the dereference of that. Which says, hey, you're getting assigned into there. Yep. Because RBX holds the pointer that was originally passed in RDX, so effectively it's that, yeah. Restore register pop quad word RBX. Undo the earlier push because this is callee saved. That means that we can't modify that. Or sorry, it's caller saved. RBX is something that cannot be changed. I guess you'd say it's Coley saved. Yeah. CFI def CFA offset 8 updates stack unwinding metadata. Stack frame shrinks back to 8 bytes. Function return. Return to the caller, equivalent to instruction pointer is equal to RSP. RSP is the stack pointer, so it's whatever is on the stack. We're returning to that location, and then we advance 8 to effectively delete it off the stack. So that would be, the ret here is part of the epilogue. End of function metadata ends the call frame info region. LFE0 local label function end used by debugging. Then down here we have size. Mult store is equal to negative mult store. Computes the size of the function. Current address minus the start address would be the size, okay? And that's just a assembler declaration, is that what they called it? Yeah, directives, assembler directive. So assembler stores a function's length and elf symbol table, okay. Compiler metadata. Ident is the compiler. No runtime effects, stack note, section, note, GNU stack, prog bits. It does a pretty good job of reversing it. Because the RDX might change is why. Hey, you got NAD. That's good. Okay. Cool. That was helpful. Let's continue reading. So each indented line in the code corresponds to a single machine instruction. For example, the push quad word push Q instruction indicates that the contents of register RBX should be pushed onto the program stack. All information about local variable names or data types has been stripped away. If we use the -C command line option, GCC will both compile and assemble the code. This will generate an object code file mstore.o that is in binary format and hence cannot be viewed directly. Embedded within the 1368 bytes of the file mstore.o is a 14-byte sequence with the hexadecimal representation so-and-so. This is the object code responsible corresponding to the assembly instructions listed previously. A key lesson to learn from this is that the program executed by the machine is simply a sequence of bytes encoding a series of instructions. The machine has very little information about the source code for which these instructions were generated. To inspect the contents of machine code files, a class of programs known as disassemblers can be invaluable. These programs generate a format similar to assembly code from machine code. With Linux systems, the program objdump for object dump can serve this role given the -D command line flag. I heard about this thing LLVM objdump. maybe play with that. Do I still have anything under here? Yeah, it looks like I do. That's a binary though. Vim makefile. We'll do one here. Because that can't be a program. There's no main. mstore. There is no main there. So if I run build mstore, it just looks like an object file. Oh, we did a touch here, that's why. Okay, I'm gonna compile with Clang. So far I'm liking Clang the most. Clang and GCC. We'll skip this, we'll do -C, I think. Oh, and this needs to be like this, sorry, my bad. And we need to go up here and we need to add it here. Say build mstore.o. Make no input files. Okay, that makes sense. Because I forgot to include mstore.c. This thing also needs... Oh no, it doesn't need anything. Make. Okay. If we do obj dump on build mstore.o. What's this thing doing here? I don't need that right now. What if I do llvm obj dump? Okay, same thing. So what do I want to do here? I want to list the disassembly. Disassemble should be -d is equal to sim. D, and this thing's called mult store. Can I do equals? Probably not. Disassemble mult store. Okay. And if I do llvm obj dump, looking at here, disassemble all sections found in input files. Don't necessarily want to do that. Disassemble symbols. So that's a difference. So this one's like that. And then if we want to do llvm obj dump, we have to say disassemble symbols. And that gives us this, both in AT&T syntax, both pretty much identical. The highlighting's a little bit different. I also heard that llvm handles the little endianness of literals better. But who knows? Because there's no immediate values in this code. Maybe open up main here, or mstore.c, and we'll do like a print or puts. No, that wouldn't work. Yeah, we do printf of %d new line, and we'll give it 1, 2, 3, 4, 5, something like that. Something that crosses multiple bytes, and we'll pound include our standard io.h, and then we'll rerun our make, and then we'll do our 2 disassemblies here, that one and that one. So look at the immediate value. First of all, it gives you a comment saying, hey, this is the immediate value. This one says 3039, that's fine, and it's reverse 3039. So not too much more helpful. This is saying load effective address quad word. So this has like a suffix. And it's saying, hey, take RDI or take the what? This is a little bit different output here. So this is saying take whatever values is in your instruction pointer, like whatever it's pointing at currently, and store it into RDI. Well, this is giving you a bunch of other crap here. Call 16 mult store. Huh? Oh, because it knows the offset already. Saying, hey, go to mult store plus 16 and call that thing over there. Okay, I think the LLVM one's a little bit better. Clean some things up. The highlighting, I guess, is a little bit nicer. Okay. Okay, let's go ahead and delete this then. Return it back to its original state. Okay, let's continue reading. To inspect the contents of machine code, yeah, we already talked about disassemblers, so we can object dump it. The result here, we have added line numbers to the left and annotations in italicized text. Okay. Disassembly of function sum in binary file umstore.o. On the left, we see 14 hexadecimal byte values listed in each byte sequence shown earlier, partitioned into groups of 1 to 5 bytes each. Each of these groups is a single instruction, with the assembly language equivalent shown to the right. Several features about machine code and its disassembled representations are worth noting. x86-64 instructions can range in length from 1 to 15 bytes. The instruction encoding is designed so that commonly used instructions and those with fewer operands require a smaller number of bytes than do less common ones or ones with more operands. The instruction format is designed in such a way that from a given starting position, there is a unique decoding of the bytes into machine instructions. For example, only the instruction push quad word RBX can start with a byte value 53. The disassembler determines the assembly code based purely on the byte sequences in the machine code file. It does not require access to the source or assembly code versions of the program. The disassembler uses a slightly different naming convention for the instructions than does the assembly code generated by GCC. In our example, it has omitted the suffix q from many of the instructions. These suffixes are size designators and can be omitted in most cases. Conversely, the disassembler adds the suffix q to the call and ret instructions. Again, these suffixes can safely be omitted. Generating the actual executable code requires running a linker on the set of object code files, one of which must contain a function main. Suppose the file main C, we had the following function. Well, we still need our bolt 2, right? Oh, the bolt 2 is in the main on the next line. Then we could generate an executable program prog as follows. So you say, hey, here's this 2C program, just generate the output prog. The file prog has grown to 8,655 bytes since it contains not just the machine code for the procedures we provided, but also code used to start and terminate the program, as well as to interact with the operating system. We can disassemble the file prog, The disassembler will extract various code sequences, including the following: disassembly of function sum and binary file prog. Yep. This code is almost identical to that generated by disassembly of mult store.c. The important difference is that the addresses listed along the left are different. The linker has shifted the location of the code to a different address range of addresses. A second difference is that the linker has filled in the addresses that the call queue instruction should use to call the function mult2. Line 4 of this assembly, one task for the linker is to match function calls with locations of the executable code for those functions. A final difference is that we see 2 additional lines of code, lines 8 and 9. These instructions will have no effect on the program since they occur after the return instruction. They have been inserted to grow the code for the function to 16 bytes, enabling a better placement of the next block of code in terms of memory system performance. Notes on formatting. The assembly code generated by GCC is difficult for a human to read. On one hand, it contains information with which we need not be concerned, while on the other hand, it does not provide any description of the program or how it works. For example, suppose we give the command to generate the file mstore.s. The full contents is as follows. All the lines beginning with dot are directives to guide the assembler and linker. We could generally ignore these. On the other hand, there is no explanatory remarks about what the instructions do or how they relate to the source code. To provide a clear presentation of assembly code, we will show it in a form that omits most of the directives while including line numbers and explanatory annotations. For our example, an annotated version would appear as follows. So we got our mult store, and then we say X is in RDI, Y is in RSI, destination is RDX, which comes from our calling convention thing. If we go here, RDI, RSI, RDX. Yep. We typically show only lines of code. We haven't read this whole thing. So we save the RBX value onto the stack. We then copy the destination to RBX so that it won't get messed up by calls to mult2. We then call mult2, and then we store the return on RAX into whatever is being pointed to by RBX, and then we restore RBX and return. We typically show only the lines of code relevant to the point being discussed. Each line is numbered to the left for reference and annotated on the right by a brief description of the effect of the instructions and how it relates to computations of the original C code. This is a stylized version of the way assembly language programmers format their code. We also provide websites to cover material intended for dedicated machine language enthusiasts. One website describes IA32 machine code. Having a background in x86-64 makes learning IA32 fairly simple. Another website gives a brief presentation of ways to incorporate assembly code into C programs. For some applications, the program must drop down into assembly code to access low-level features of the machine. One approach is to write entire functions in assembly code and combine them with C functions during the linking stage. A second is to use GCC support for embedded assembly code directly with C programs. So you got this aside on AT&T versus Intel assembly code formats. In our presentation, we show assembly in the AT&T format named after AT&T, the company that operated Bell Laboratories for many years. The default format for GCC, object dump, and other tools we will consider. Other programming Tools, including those from Microsoft, as well as documented from Intel, show assembly code in Intel format. The two formats differ in a number of ways. As an example, GC can generate code in Intel format for the sum function using the following command line: masm is equal to Intel. This gives the following assembly code. We see that the Intel and AT&T formats differ in the following ways. The Intel code omits the size designation suffixes. We see instruction push and move instead of push Q and move Q. The Intel code omits the % character in front of register names, using RBX instead of %RBX. The Intel code has a different way of describing locations in memory, for example, quad word pointer RBX rather than just dereferencing of RBX. Instructions with multiple operands list them in reverse order. This can be very confusing when switching between two formats. That's the main difference, is the operand ordering. Although we will not be using Intel format in our presentation, you will encounter in documentation from Intel and Microsoft. Data formats, due to its origins as a 16-bit architecture and expanded into a 32-bit one. Wait a minute. Okay, yeah. Intel uses the term word to refer to a 16-bit data type. Based on this, they refer to 32-bit quantities as double words and 64-bit quantities as quad words. Figure 3.1 shows the x86-64 representation used for the primitive data types of C. Standard int values are stored as double words, 32 bits. Pointers, shown here as char star, are stored as 8-byte quad words. As would be expected in a 64-bit machine, with x86-64, data type long is implemented with 64 bits, allowing a very wide range of values. Most of the code examples in this chapter use pointers and long data types, and so they will operate only on quad words. The x86-64 instruction set includes a full complement of instructions for byte words and double words as well. So you got C declarations: char, short, int, long, char star, float, and double. So char is a byte. Could be signed or unsigned depending on implementation. Assembly code suffix would be a B. Its size is 1 byte. A short is a word. Makes sense. 16 bits, 2 bytes. W. Size 2. Int is a double word, which is a L suffix. Okay, I wasn't familiar with L. And it's 4 bytes. Long is a quad word. Q, which is 8 bytes. Char star is a quad word. Q, 8 bytes. A float, single precision, is a S, 4 bytes, not an L. And a double is an L, which is 8 bytes. That's confusing as fuck. Webaside. ASM, EASM. Combining assembly code with C programs. Although a C compiler does a good job of converting the computations expressed in a program into machine code, there are some features of machine that cannot be accessed by a C program. For example, every time an x86 64-bit processor executes an arithmetic or logical operation, it sets a 1-bit conditional flag named PFF, or parity flag. To 1 when the lower 8 bits in the resulting computation have an even number of ones, and 0 to otherwise. Computing this information in C requires at least 7 shifting, masking, and exclusive OR operations. Even though the hardware performs this computation as part of every arithmetic and logical operation, there is no way for C program to determine the value of PF conditional code flag. This task can readily be performed by incorporating a small number of assembly code instructions into the program. There are 2 ways to incorporate assembly code into C programs. First, we can write an entire function as a separate assembly code file, and then let the assembler and linker combine this with code we have written in C. Second, we can use the inline assembly feature of GCC, where brief sections of assembly code can be incorporated into a C program using the ASM directive. This approach has the advantage that it minimizes the amount of machine-specific code. Of course, inline assembly code in a C program makes a code specific to a particular class of machines, such as x86-64, and so it should only be used with the desired feature can only be accessed this way, and probably should be hidden behind a pound define type check. That's interesting website though. Let's go ahead and pull up the README. Do I have any jobs here? No, them. README. This is called the aside ASM EASM. Oops, please go away. EASM. Okay. Okay. Let's continue reading. Floating point numbers come in two principal formats: single precision values, which are 4-byte, and corresponding data type of float, and double precision, which 8-byte values corresponding to C data type double. Microprocessors in the x86 family historically implemented all floating point operations with a special 80-bit 10-byte floating point format. This format can be specified in C programs using declaration long double. We recommend against using this format, however. It is not portable to other classes of machines, and it is typically not implemented with the same high performance hardware as is the case for single and double precision arithmetic. Oops. Alright. As the table figure 3.1 indicates, most assembly code instructions generated by GCC have a single character suffix denoting the size of the operand. For example, the data movement instruction has 4 variants: move B, move W, move L, move quad word. Suffix L is used for double words, since 32-bit quantities are considered to be long words. The assembly code uses the suffix L to denote a 4-byte integer, as well as an 8-byte double precision floating point number. This causes no ambiguity, since floating point codes involve an entirely different set of instructions and registers. Okay. Accessing information. An x86-64 central processing unit CPU contains a set of 16 general purpose registers storing 64-bit values. These registers are used to store integer data as well as pointers. Figure 3.2 diagrams the 16 registers. Their names will begin with %R, but otherwise follow multiple different naming conventions. Owing to the historical evolution of the instruction set, the original 8086 had 8 16-bit registers shown in figure 3.2 as registers AX through BP. Each had a specific purpose, hence they were given names that reflected how they were used. With the extension to IA32, these registers were expanded to 32-bit registers labeled EAX through EBP. In the extension 64-bit, the original 8 registers were expanded to 64-bit labeled RAX through RBP. In addition, 8 new registers were added, and these were given labels according to a new naming convention, R8 through R15. As nested boxes in figure 3.2 indicate, instructions can operate on data of different sizes stored in the lower order bytes of the 16 registers. Byte level operations can access the least significant byte. 16-bit operations can access the least significant 2 bytes, 32-bit operations can access the least significant 4 bytes, and 64-bit operations can access entire registers. In later sections, we will present a number of instructions for copying and generating 1, 2, 4, and 8 byte values. When these instructions have registers as destinations, two conventions arise for what happens with the remaining bytes in the register for instructions that generated less than 8 bytes. Those that generate 1 to 2 byte quantities, leaving the remaining bytes unchanged. Those that generate 4 byte quantities set the upper 4 bytes to the register to 0. Those that generate 4 byte quantities set the upper 4 bytes to the register as 0. The later convention was adopted as part of the expansion from IA32 to x86-64. As the annotations along the right-hand side of figure 3.2 indicate, different registers serve different roles in typical programs. Most unique among them is the stack pointer, the RSP, used to indicate the end position in the runtime stack. Some instructions specifically read and write to this register. The other 15 registers have more flexibility in their uses. A small number of instructions make specific use of certain registers. More importantly, a set of standard programming conventions governs how the registers are to be used for managing the stack passing function, arguments, returning values from functions, and storing local and temporary data. We will cover these conventions in a presentation, especially in section 3.7, where we describe the implementation of procedures. So we got this big table here. And okay, I didn't know that the new registers, the R8 through R15, were something that you could address the lower 8 bits and the upper, or the lower 1 byte, 2 byte, and 4 bytes of the register. And you do this through R8 double and R8 word and R8 byte, which makes sense. Okay. Operand specifiers. Most instructions have one or more operands specifying the source values to use in performing an operation and the destination location into which to place the result. x86-64 supports a number of operand forms. See figure 3.3. Okay, let's look here. So you have an immediate operand, which is a $sign with the immediate value, and then the operand value will be that exact value. It's called immediate. And then we have register. So these usually have percent in front of them. And then we got all the memory stuff. So we have an immediate memory address, which is usually part of 0x, and that accesses that. Absolute. Okay, sorry, I just was reading over that table. Okay, let's continue reading here. Source values can be given as constants and read from registers or memory. Results can be stored in either registers or memory. Thus, the different operand possibilities can be classified into 3 types. The first, immediate, is for constant values. The AT&T format assembly code, these are written with a $sign followed by an integer following standard C notation. For example, $-577 or $0x1f. Different instructions allow different ranges of immediate values. The assembler will automatically select the most compact way of encoding a value. The second type, register, denotes the contents of a register. One of the 16, 8, 4, 2, or 1 byte low order positions of the register for operand having 64, 32, 16, or 8 bits respectively. In figure 3.3, we use the notation R sub x to denote an arbitrary register A, R sub A to denote an arbitrary register A and indicate its value with the reference R indexed into RA. Viewing the set of registers as an array R indexed by register identifiers. The third type of operand is a memory reference, in which we access some memory location according to a computed address, often called an effective address. Since we view the memory as a large array of bytes, we use the notation M adder to denote a reference to the B byte value stored at memory address, or in memory starting at address adder. To simplify things, we will generally drop off the subscript B. As figure 3.3 shows, there are many different addressing modes allowing different forms of memory references. The most general form is shown in the bottom of the table with the syntax immediate RB RIS. Such a reference has 4 components: an immediate offset M, a base register RB, an index register RI, and a scale factor S, where S must be 1, 2, 4, or 8. Both the base and an index must require 64-bit registers. The effective address is computed as immediate plus the R sub B plus R sub I times S. This general form is often seen when referencing elements of an array. The other forms are simply special cases of this general form where some of the components are omitted. As we will see, the more complex addressing modes are useful when referencing array and structure elements. Assume the following values are stored at the indicated memory address and register. Oh, it's a problem. Yay, our first problem. We'll just do problems.md, and we'll do what? This is 3.1, and we have a table. So this is going to be assume the following values are stored at the indicated memory address and registers. So we got address, we got value, register, value. Okay. Fill in the following table showing the values for the indicated operands. So this is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Plus, yeah, this would be 10. By 2. So table, set size, 10 by 2. Bam. And there's no way of clearing this stuff, so I'll just type it in here. We'll say operand and value. And this is going to be %RX. This is going to be 0x104. Which will be, yeah, okay. Then here we got $0x108. 9 will be %RX. This will be 4 of %RX. This will be 9 of %RX RDX. Oops, an extra C in there somehow. This will be 260 of %RCX %RDX. This will be 0xFC of comma %RCX 4, and then percent REX, percent RDX, 4. Okay, so this is going to be the value. If I go up, can I just click on this and have it not be a complete piece of shit? There we go. All right, so REX, according to that table, is going to be 0x100. And then saying 0x104 would be an access at the memory address 104, which would be 0xAB. This would be 0x108, so it's an immediate value. RDX, we're going to take RDX and dereference it. So 03, sorry, RAX, which is 100, which would be 0xFF. 4 REX, so it's going to be taking REX and then adding 4 to it, I believe. Let's go back to the table. Yeah, adding 4 to that value. So that'd be 0xAB. If I can type here, 0xAB. Then 9 RAX RDX. I think this is base, and so RAX would be the base 100. RDX would be the offset 3. And then we add 9 to that. So it would be 3 plus 9 would be 12, which would be C, which would be 0x11. This one will be, it's kind of hard to see. Do it like that. 260 plus RCX, which is 1. And then RDX, which is 3. So we got 4 plus 260 would be 264. We don't know the value there. So let me just confirm. Yeah, those are just added together, all 3 of them, yeah. RCX is 1, RDX is 3, so it's 4. So it'd be 264. Assume the following values are stored in indicated memory address and registers. What the hell is 264 though? Oh, it's 260, but in we have to convert that into hex. So if we just say Python 264 into hex. Oops. Typo. There we go. 108, which would be 0x13. Okay. Get rid of that. So now we have this other form with the bases removed, which is just multiplication of the 2. So here would be RCX times 4, which is 1 times 4 would be 4, plus FC. So we're going to say Python here, Python, and we're going to say 0xFC plus 4, and convert that into hex, and that gives us 100, which is 0xFF. And then we have our final one, which is all 3 values excluding the immediate, which is addition and then multiplication. Makes sense. REX and RDX, which would be 103. Wait a minute. RAX is 100. RDX is 3. 103 times 4. So this would be, but it'd be in a hex 0x103 times 4. and then that whole thing in hex. That's going to be 40C, which isn't in the range. Yeah, let's go back to the table, make sure we got this right. So you got base plus, oh, but multiplication has a higher precedence, at least in C. So you do the multiplication first and then add the value. So it'd be RCX, 1 times 4 would be 4. Sorry, RDX. Yeah, this is my bad. So RDX is 3. Multiply that times 4 would be 12, which is C. Hex, or 0x C, which is 12. So you got 0x C plus RAX, which is 100, which is going to be 100C. So that's 0x11. 0x11. Okay. Let's go ahead and check these values, make sure we got them right. So this is chapter 3, and there should be, it's homework problems. I think we want to get past all that. Practice problems, here we go. That was very close. Practice problems. It doesn't say what type comment it is. Okay. 100 AB, 108 FF. Yep. AB 1113, AB 1113, FF 11. Yep, got it right. Generate. Copy to clipboard. Paste. Quit. Quit out that. That should be good. Okay. Let's move on to data movement instructions. Among the most heavily used instructions are those that copy data from one location to another. The generality of the operand notation allows a simple data movement instruction to express a range of possibilities that in many machines would require a number of different instructions. We present a number of different data movement instructions differing in their source and destination types, what conversions they perform, and other side effects they may have. In our presentation, we group the many different instructions into instruction classes. Where the instruction in the class performs the same operation but with different operand sizes. Okay. Figure 3.4 lists the simplest form of data movement instruction, move class. These instructions copy data from a source location to a destination location without any transformation. The class consists of 4 instructions: move B, move W, move L, move Q. All 4 of these instructions have similar effects. They differ primarily in that they operate on data of different sizes, 1, 2, 4, and 8 bytes, respectively. There's move absolute quad word. So we have source and destination, immediate into register. The source operand designates a value that is immediate, stored in a register, or stored in memory. The destination operand designates a location that is either a register or a memory address. x86-64 imposes the restriction that a move instruction cannot have both operands refer to memory locations. Copying a value from one memory location to another requires 2 instructions. That's something I remember from reading or learning about assembly back in like 2018. Just go ahead and highlight that, even though I already knew it. Refreshing my neurons here. Copying a value from one memory location requires 2 instructions. The first, let me highlight that part too. First, to load the source value into a register, and the second to write the register value to destination. Referring to figure 3.2, register operands for these instructions can be the labeled portion of any of the 16 registers, where the size of the register must match the size designated by the last character of the instruction. B, W, L, or Q. For most cases, the move instruction will only update the specific register bytes or memory locations indicated by the destination operand. The only exception is when move L has a register as a destination, it will also set the high order 4 bytes of the register to 0. This exception arises from the convention adopted in XA664 that any instruction that generates a 32-bit value for a register also sets high order portion of the register to 0. The following move instruction examples show the 5 possible combinations of source and destination types. You recall that the source operand comes first and the destination second. So this is an immediate value into a register. Since EAX, it's 4 bytes. This is a register. This will be 2 bytes. Yep. This is a move. Oh, and they have the suffixes already. So a move byte, but the byte is stored at the dereferencing of RDI plus RCX, and we're storing it in the AL register. Yep, 1 byte. There's another immediate value into the memory pointed to by ESP, and that's a 32-bit dereference. So that's immediate to memory, and because it's move B, it's a byte. Move quad word, so that's taking the value, the 64-bit value in RAX, and moving it to the location pointed to by the base pointer minus 12. So this would be like, writing to the stack, basically. A final instruction documented in figure 3.4 is for dealing with 64-bit immediate data. The regular move quad instruction can only have immediate sources operands that can be represented as 32-bit 2's complement numbers. This value is then signed extended to produce a 64-bit value for the destination. The move abs q instruction can have an arbitrary 64-bit immediate value as its source operand and can only have a register as the destination. So that's a way of initializing a register from source that's stored in memory. So it's really copying a value that's in the memory because the instructions are in the memory. But I guess if you're doing the prefetching of all the instructions, it'll be in the cache somewhere. Okay, figure 3.5 and 3.6 document 2 classes of data movement instructions for use when copying a smaller source value into a larger destination. All these instructions copy data from a source, which can be either registered or stored. Register or stored in memory to a register destination. Instructions in the move Z. So these are all move Z. So you got move the absolute, the regular move with the suffixes, the move abs quad word, which does what you would think it does. And then you got this move Z with 2 suffixes, it looks like. So that's 0 extended. And it's moving from source to a register. So this is a way of like explicitly asking for 0 extended. These instructions have register or memory locations as the source and a register as the destination. Yeah. Instructions of the MoveZ class fill out the remaining bytes of the destination with zeros, while those in move S class, there's a move S as well, fill them out by sign extension, replicating copies of the most significant bit of the source operand. Observe that each instruction name has sign designators as its 2 final characters, the first specifying the source size and the second specifying the destination size. As can be seen, there are 3 instructions in each of these classes, covering all cases of 1 and 2 byte source sizes and 2 and 4 byte destination sizes, considering only cases where the destination is larger than the source, of course. Of course. So this is sign extending data movement instructions. The move S instruction have a register or memory location as a source of a register and a register as a destination. The CLTQ instruction is specific to registers EAX and RAX. So you got all of our instruction variants here. They basically take a source, they sign extend it, and write it into register. And then there's a specific CLTQ. It's specific to registers EAX and RAX. So it takes whatever is in EAX and sign extends it into itself, basically, because it's shared space. Note the absence of an explicit instruction to be 0 extended a 4-byte source value to an 8-byte destination in figure 3.5. Yeah, let's go back to that table. So we have byte to word, so that's byte to 2 bytes, a byte to 4 bytes, a 2 byte to 4 bytes, a byte to a quad word, and a 2 byte to a quad word. And it's talking about 4-byte source, which would be a, so you got byte, word, and long. So there are no sources that are longs going to 64-bit, because that's what the architecture already does. You don't have to do a sign extension or 0 extension when the architecture does that by default. Such an instruction would logically be named move ZLQ, but that instruction does not exist. Instead, the type of data movement can be implemented using a move L instruction, having a register as the destination. This technique takes advantage of the property that the instruction generated by a 4-byte value with the register as the destination will fill up the upper 4 bytes with zeros. Otherwise, the 64-bit destination's moving with sign extension is supported for all 3 source types, and moving with 0 extension is supported for the 2 smaller source types. Figure 3.6 also documents the CLTQ instruction. This instruction has no operands. It always uses register EAX as a source and RAX as a destination for the sign extended result. It therefore has the same exact effect as the instruction move LQ EAX RAX, but it has more compact encoding. Okay, practice problem. Yay, more practice. I actually like these problems. They're very practical versus the math stuff. For each of the following lines of assembly language, determine the appropriate instruction suffix based on the operands. For example, move can be written as move B, move W, move L, and move Q. Oh, cool. So how many do we have here? 1, 2, 3, 4, 5, 6. We'll just do 1, 2, 3, 4, 5, 6. Come on. RF. There we go. Okay, A. So this is going to be the 64-bit register. We're going to read that as an address, dereference it, and store it in EAX. So that's going to be a 32-bit value. So this would be long. Yeah, long. This is saying take the value that's in DX and store it in the 64-bit dereferences of that. The DX would be a 16-byte, which would be a W. The C here. Oh shit, I did that in reverse. I did that in reverse, but I think it still doesn't matter. So if we take EAX and store it into the thing pointed there, Doesn't matter, it's still 32-bit. And same thing for the 16-bit. So now we have an immediate value, which is 8-bit, a single byte. And we're storing it into a, what is this, a 2-byte? I think that's still 2 bytes, which would be what? A word. I think that's still a word. So we got some math that we do on our address, and we store it, so that's another word. And then this one, maybe B. That is a 64-bit, so that's a quad word. And then you have on the last one a 16-bit value, so that's going to be a word. I'm going to go with B on this, because I think it'll just do the low order bits on that, but it might be W. I'm pretty sure it's B, but we'll see. 3.2 answers. As we have seen, the assembly code generated by GC includes suffixes on these instructions, while disassembler does not. Being able to switch between these two forms is an important skill to learn. One important feature is that memory references in x86-64 are always given with quad word registers, such as RAX, even if the operand is a byte, single word, or double word. So LWBBQW, LWBBQW. So C was indeed B, but why was D B? Let's try to figure that out before we move on here. We compute a address. Doesn't matter where it is, some location in memory, and we take how many bytes. Shouldn't that be a DL? Oh, because these are L's. And if we go back to that register thing, a DL is the first byte. Yep. So that's B, but for different reasons. Yeah. Basically, like what I learned just now is that if you have a 2-character register, you have to see what the suffix is, because I've always looked at those as AX, BX, CX, DX, SI, DI, BP, SP. But you can have the first 4 registers, if they have AL, BL, CL, DL, those are the single byte versions of those registers. So today I learned. Alright, so the next one is 3.3, which is the next page. Go over here. Each of the following lines of code generate an error message when we invoke the assembler. Explain what is wrong with each line. Okay. You got 1, 2, 3, 4, 5, 6, 7 different lines. So, oops. I want to get used to not using the mouse to switch my view. Because I feel like it's a handicap. 1, 2, 3, 4, 5, 6, 7. Yep. So the first one, we're saying move a byte. We give it a nibble. My guess is that, and I wouldn't guess it's an error, but I'm not really familiar with assembler, but immediate value is only 4 bits. B, move long, which is 32 bits. So it's saying, hey, move a 64-bit value into memory. RAX is 64 bits, but move was 32. Number 3, so we're saying, hey, take whatever this address is a word, which is 16 bits, and store it into RSP. We'll say RSP is 64 bits, but move was 16. We'll say destination. Destination. C. Wait a minute. Alright, so we got D. AL going into SL. L, again, now I know is a byte. So you can't... Wait a minute, move B? Why is that going to fail? Let's go back to our table. AL to BL. And move B is a byte. Sorry, AL to SL. Where's SL? That's PL. I would say SL is not a register name, because it's SIL. Not a register. E. RAX 64-bit move quad word into you can't move into a F is going to be move long 32-bit EAX value into RDX. That seems valid because RDX we'll just say RDX. A destination percent RDX is 64 bits, but MOV was 32. Which is the same thing as B. Wait a minute, this is wrong. Let's go through these again because I fucked up B, and now I figure I might have fucked up all these. So we're moving a single byte, but our immediate value is a nibble. So immediate value is only 4 bits, but MOV was 8. Our move L RAX is saying move the 64-bit value into RSP's location. So this is a source RAX is 64-bit, not destination. Source RAX is 64 bits, but move was 32. C is move 16, but our destination RSP plus 4, that's fine. Why is that? I think I might have misunderstood this one. This one's I'm not sure about. This one, AL and SL. SL is not a registered name. Let's check the registered names RAX and RSP. RAX is, yeah, and there is, yeah, RSP down here, stack pointer. They're both 64-bit values, but they're both being dereferenced. There's a form of immediate move W. That should be valid. I don't know why that's invalid, to be honest. Okay, so next one is move quad word RAX. Yeah. Can't move an immediate value. That's obvious. The move long is 16. And we're moving 32 into 64. So our DX is 64 bits. Move was, oh no. Move was 16. Our DX is 64 bits. And source was 32 bits. But MOV was 16. And then finally a byte in SI. If we go back to our thing, SI is not a valid instruction. Or no, it is. SI is a valid register, 16 bits into this place in memory. So I'm going to say source SI is 16 bits where but the MOV was 8. So why is C messed up? I thought I had that, but I don't think I do. So we have a 64-bit address in RAX. We dereference it, so it's just pointing to some place in memory. And then we do the same thing at RSP plus 4. Move W. I don't know. I don't know why that is. We'll have to let the answers tell us. 3.3. Since we rely on GC to generate most of our assembly code, being able to write correct assembly code is not a critical skill. Nonetheless, this exercise will help you become more familiar with the different instructions and operand types. Here's a code with explanations of errors. So MOV B immediate into EAX or EBX. Cannot use EBX as address register. Okay. You can use EBS as an address register x86. In fact, it's one of the classic registers used for addressing. The confusion usually comes from context, searching for 64-bit, or special conventions like pick and got. assembles. Each of the following lines of code generates an error when we invoke the assembler. Well, let's just do them all here. I have them in the source, or in the PDF here. Okay. So 5 was fine. 6, incorrect register, REX used with L suffix. And I'll just do a split here and say them jump chapter CSAPP. Problems. Oops. Okay. So my answer was source REX is 64 bits, but MOV was 32. Yeah, which is exactly what it says there. Mismatch between instruction suffix and register ID, yeah. So let's go to C here, which I didn't know. Operand type mismatch for MOV. Can I have both source and destination be memory references? Oh, that's right. Forgot about that. So I just wrote that, or I just highlighted that in the book, and I messed it up. All right. So in the book on 4, it says no register named SL, and that's what I said. Cannot have immediate as destination. Yeah. F is destination operand is incorrect size. Yeah, pretty much what I said, and then I messed up how to spell source here. So then last one, mismatch between instruction suffix and register ID. Yeah. Okay. So I got most of those right. The one that I didn't know, I knew, but I just didn't see when I read it. I was like, oh, it's just a memory address and a memory address. What's wrong? It's like, yeah, they can't both be memory addresses. That's the third time you've learned that. And it hasn't stuck, obviously. And then the first one, actually, it doesn't generate an error when assembling, so there's no issue with it. Unless I'm missing something. No, I copied it straight from the book. So, okay. Data movement example. I'll put my bookmark back in here and continue on. As an example of code that uses data movement instructions, consider the data exchange routine shown in figure 3.7, which is over here on the next page. Both the C code and assembly code generated by GCC. So let's look at that. So we got the C code is a function exchange. It takes in a pointer to a long and a long value and returns a long value. The implementation dereferences the first argument, assigns it to x, and then assigns y into that value, and then reads out x. That makes sense. The assembly code exchange, xp in RDI and y in RSI. So we say, hey, we're going to move quad word from RDI, whatever that value is, dereference it, assign it to REX. Move quad word of whatever's in RSI into RDI, and then return, leaving RDI, or sorry, REX as the return value. Wait a minute, let me reread this. RDI and RSI. So we're saying dereference RDI and assign it to REX. So REX must be the return value, which if we go back to our bookmark here, RAX, where is it? Return value, yeah. Okay. Cool. That all makes sense. So let's go back to the text. As an example of code that uses data movement instructions, consider the data exchange routine followed and shown in figure 3.7, both as C and assembly code generated by GCC. As figure 3.7b shows, function exchange is implemented with just 3 instructions, 2 data movements plus an instruction to return back to the point from which the function was called, ret. We will cover the details of function call and return in section 3.7. Until then, it suffices to say that arguments are passed to functions in registers. Our annotated assembly code documents these. A function returns a value by storing it in register REX or in one of the lower order portions of this register. When the procedure begins execution, procedure parameters xp and y are stored in registers RDI and RSI respectively. Instruction 2 then reads x from memory and stores the value in register REX. A direct implementation of operation x is equal to star xp in the C program. Later, register REX will be used to return a value from the function, and so the return value will be x. Instruction 3 writes y to the memory location designated by xp in register RDI. Direct implementation of the operation of dereference of xp is assigned into by the value at y, which is in register. This example illustrates how the mov instruction can be used to read from memory to a register and to write from a register to memory. 2 features about this assembly code are worth noting. First, we see that we call pointers in C are simply addresses. Dereferencing a pointer involves copying that pointer to a register and then using this register in a memory reference. So dereferencing a pointer involves copying that pointer to a register and then using this register in memory at reference. I'm going to highlight that. So it has to be in a memory reference to dereference it. Or sorry, it has to be in a register to dereference it. Second, local variables such as x are often kept in registers rather than stored in memory locations. Like the stack, register access is much faster than memory access. Assume variables sp and dp are declared with types source and destination t, where source t and destination t are data types declared with type def. We wish to use the appropriate pair of data movement instructions to implement the operation. Pointer to sp of type destination t into dereference of dp. Okay. Oh, I forgot to read the aside over here. I've been skipping asides. Let's go back because I want to read the asides that I skipped, which is on 220. Understanding how data movement changes a destination register, which is here. Okay, there's two asides I skipped, so I'll come back to those. I'll be right back though. All right, understanding how data movement changes a destination register. Did we read this already? No, I don't think so. As described, there are two different conventions regarding whether and how data movement instructions modify the upper bytes of a destination register. This distinction is illustrated by the following code sequence. So we move the abs quad word of some really long hex string into RAX, which just does the assignment, as we expect. Then we do a move byte of -1, which is all F's. We're just going to put two F's at the AL location, which would be this first byte, and we leave the other bytes changed. Yep. Move W behaves the same way, but with a W, a word size 16 bytes, 16 bits. EX 32 bits does the same thing, but then we do -1 into RAX. Sorry, if we do the move L into EAX, it's going to do the 0 fill. And if we move quad word, it just obviously sets everything. In the following discussion, we use hexadecimal notation. In the example, the instructions on line 1 initialize the register RAX to the pattern so-and-so. The remaining instructions have immediate value -1 as their source values. Recall that the hexadecimal notation -1 is the form of FFF, where the number of F's is twice the number of bytes in the representation. The move B instruction in line 2 therefore sets the low order byte of RAX to FF, while the move W instruction sets the low order bytes to FFFF, while the remaining leaving with the remaining bytes unchanged. The move L instruction in line 4 sets the low order bytes to F's, but it also sets the high order bytes to 0. Finally, the move quad word instruction sets the complete register to F. So that's like, this is the strange behavior here. And I guess they did it for compatibility reasons. Not really sure. Okay, next aside, comparing byte movement instructions. So the following example illustrates how different data movement instructions either do or do not change the high order bytes of the destination. Observe that the 3-byte movement instructions move B, move S, BQ, and move Z, BQ differ from each other in subtle ways. Here's an example. Okay, so we're moving absolute value into REX, just assigns it in there. We say, hey, move byte. Here's the byte into DL, which is a long register, which is no, it's a byte as a byte register. Move byte DL to AL, and AL is the. If we go back to our table. AL is the first byte of REX, which will set that appropriately, yep. And then we're going to move signed byte to quad word. So this is sign extension on A, which is all F's because the sign is there. And then 0 extension on the other one, which just does zeros. In the following discussion, we will use hex as notation for all the values. The first 2 lines of the code initialize register REX and DL to this big value and A respectively. The remaining instructions will copy the low order byte of RDX to low order byte of REX. The move B instruction does not change the other bytes. The move SB instruction in line 4 sets the other 7 bytes to either all ones or all zeros depending on the high order bit of the source byte. Since hexadecimal A represents binary value 1010, sign extension causes the higher order bits to each be set to FF. The move Z BQ instruction in line 5 always sets the other 7 bytes to 0. Makes sense, nothing surprising there. So we were all the way over on this side. Let's read that aside. Okay. Some examples of pointers. Function exchange provides a good illustration of the use of pointers in C. Arguments xp is a pointer to a long integer while y is a long integer itself. The statement long x is equal to star xp indicates that we should read the value stored in the location designated by xp and store it as a local variable named x. This read operation is known as pointer dereferencing. C operator star performs pointer dereferencing. The statement xpy does the reverse. It writes the value of parameter y at the location designated by xp. It's also a form of pointer dereferencing and hence the operator star, but it indicates a write operation since it is on the left hand side of the assignment. The following is an example of exchange in action. So A is equal to 4, then we say, hey, exchange the value located at 4 with 3 and assign it back to B. So now A is going to be equal to 3 and B is going to be equal to 4. Yep. The C operator ampersand also called the address of operator creates a pointer, in this case the location holding local variable A. Function exchange overwrites the value stored with in A with 3 but returns the previous value 4 as the function value. Observe how by passing a pointer to exchange it could modify data held at some remote location. Yeah, makes sense. Oh, I think I might have skipped over this. We have practice problem 3-4 now. Actually, let me quit out of this. I don't need this. Jobs, then problems. Okay, let's do 3.4. And here, assume the variables SP and DP are declared with types. Where source and destination types are declared with type def, we wish to use the appropriate pair of data movement instructions to implement the operation SP-DP. So we're trying to assign the value that located at SP into the location DP. Assume that the values SP-DP are stored in registers RDI and RSI respectively. So we're going from RDI to RSI. RDI to RSI, So we need to save this to a register. So it's going to be some type of mov of the value located at RDI into, not RSI because we can't do that, into, did I have to do a comma on these? Yeah, comma. Into like, what was the one that everyone was saying that, let's see, will not be changed. Or BX. When calling a function, when writing a function, used freely. Okay. We'll say REX. REX. And then we can move from REX to RSI, assuming this is a quad word. We'll do a move Q here just to indicate that. And okay. Assume that the value, sorry, let's go to the next page here. Assume that the values of SC and DP are stored in registers RDI and RSI, respectively. For each entry in the table, show the two instructions that implement the specified data movement. The first instruction sequence should read from memory, do the appropriate conversion, and set the appropriate portion of the register REX. Second instruction should then write the appropriate portion of REX to memory. In both cases, the portion may be REX, EAX, AX, or AL. They may differ from one another. Recall that when performing a cast that involves both a size change and a change in signedness in C, the operation should change the size first, section 226. So we're going from a long to a long, and a long is how many? On 64-bit, a long is a quad word, because an int is 32, long is quad word. So we do move quad word, RD is literally what I have here into REX, move quad word, REX, and RSI. Okay, so then we got 1, 2, 3, 4, 5, 6. So we'll call these A, B, C, D, E, F. So A here, it's going to be a char into destination. Shit. Well, the char of RDI, let's go back to that table. This table's really handy. I'm going to earmark this because I keep on coming back to it. Okay. So RDI, is that the calling convention for the first integer argument, RDI. So we want to read just a char, which is a byte. So that would be DIL. DIL. So DIL, so it says, hey, read this. Oh no. Because RDI is the address. We dereference it. How do we convert that to a... I guess we just do, when we're doing the assignment into RAX, we need to zero out everything. When I copy one byte with zeroing out. So that would be mov 0. Yeah. 0 byte to quad word from RDI to the quad word. I think that would work. And then RSI, what's the location there? Let's go back. I'm very lost here. Alright, so it's going to an int which is 32 bits. So really we don't even need to do a quad word. We can do a EAX type thing, right? Because they're going from, this will be char 8 to int 32. So we don't even have to touch quad words, right? So we're going to say move 0 byte to long BL into RAX, but we're going to do RAX, which is EAX, obviously. EAX. And then we're going to move, not quad word, we'll move long EAX into the place that's pointed to by RSI. I think that would be correct. Let's verify that. So I'm going to go to the answers here. So long to long was given to us. Oh, we have to do the sign BL, not the 0 BL. Because it could be a 2's complement. Yeah. Move sign BL. RDI into EAX. Move L. EAX into RSI. So I got everything except for it was a move sign. Okay. What's B? B is going to be char to unsigned. Char to unsigned, which is 32. So it's going to be the same thing, except this is going to be our 0. So we need to 0 out the high order bits. Yeah, I believe that's correct. So B is going to be, no, it's still signed. Well, I think that's wrong. Oh, is it? Well, let's go ahead and just try it in Godbolt. So let's bring up Godbolt. And we're going to do C, good old C. Delete all this shit here. And it's going to be a void function. It's going to take in the char and a unsigned. And then we're not going to return anything, but we're going to have this conversion of star dp is equal to a destination t. So this is going to be a unsigned star sp And we'll do it like this: SP char star SP unsigned star DP. Yeah, okay, it compiles. So, wow, there's a lot of stuff going on here. Can I change this to AT&T syntax? There we go. So we got where's RDI? So putting RDI into the stack at RBP -8. RDI is never referenced after that. So this is like an alias for RDI. So we say, hey, RDI, we're just going to move your entire value into RAX. And this is going to be the point, or your entire value into RAX. Where they're going to we're going to do a move 0. Yeah, it does do a move 0. I was right. A move 0 of the dereference of that into EAX. And then this does a move signed of AL into EDX. RDI, RS, where's our RSI is now -16. This is RSI. I don't know why it puts everything on the stack. It seems like super. Maybe do compile options -OG. Will that help? Yeah. Okay, so this is where it does do a signed. Okay. RDI into EAX. And then EAX to RSI. Okay. Are there any comments on why? Convert the char into an int, store 4 bytes. Okay. What's our next one? So we got C here is going to be our char to, we already did char to unsigned. Okay, that's the one we were doing here. So unsigned char too long. Unsigned char too long. Unsigned char is still 8. Long is 64. So unsigned char 8. Move Z. This has to be Z. Byte to quad word. RDI to RAX. And then, because this unsigned char, we 0 extend it. Why sign extend it? Pretty sure we 0 extend it. And then we do a dereferencing of that into RAX, and then RAX just gets stored into the dereference of RSI And the fact that it's a long, I don't think matters, because the bit pattern is just the same. Okay, let's go ahead and write that. And we'll switch back to Godbolt. We'll do, instead of a char, we're doing an unsigned char. And then this is being a float. And this will be a float. So we do our move ZBQ. So they're doing some other instructions I'm not familiar with yet. Let's see what the book says for C. Move BL. Into EAX. And then move quad word EAX. RSI. Shouldn't that be? Okay, I think what happens here, so this is the answer that the book gave, is to move zero extended RDI into EAX and then move RAX into RSI. Okay, so I think what's happening here is, so we take whatever value is at RDI, that RDI is pointing to, and we move that from memory into EAX. And when we do that with move ZBL. So we're moving a byte of memory into the long EAX, and we're zero extending it. And that effectively has the effect of zero extending it all the way to a quad word, because when you're storing into a 32-bit value register, the 64-bit version of that gets its zeros set. So then all of its zeros are set on the left-hand side, and we could just move RAX into RSI, and it's safe. That makes sense. Okay. That's not what they did. They used some shit with like XMM registers, which I'm not familiar with. Okay, let's do the next one. So let's pull this down here. So that was unsigned char to long. We're doing int to char here. So I int to a char, so obviously this is 8, it's a signed 8, or yeah, it's signed 8. And then int will be what? A long, which is 32. Saying, hey, cast this 32-bit value into a char and assign it in. Let's go back over to here. Where are we? Okay, here. So he's saying cast into a char. I think you drop the most significant bytes when you do that. So int 32. Couldn't we just move B of RDI, which is, go back to my earmarked page here. RDI is DIL, DIL, into, we just need a byte of EAX. which would be AL. And then we can move byte AL into wherever RSI is pointing. I think that would work. We're saying, hey, take the low order byte, assign it to a register, and then assign it directly into RSI. Okay. Let's look up D, which is int32 to char8. It says move long to read 4 bytes. And then AL into RSI. I think the same thing would work with my version. I think my version's fine. The next one is what? Is going to be, just did int32 to char8. This is going to be unsigned 32 to unsigned char8. Oops. Okay, so this is going to say, hey, I got an unsigned 32-bit, I'm trying to go to 8. So RDI, going back to this page. Where the hell is that page? There it is. I need those little bookmark readers. I'm going to grab those. They're going to help me get back to this page. So I'll be right back. I got these little like sticky tab things here. They're kind of like mini post-it notes for when you're reading. So I'm going to use them. Okay, they go from this end. And I'm going to stick it right here. There we go. Okay, which one are we on now? Put these back. These might come in handy later though, so I'm going to keep them right there. Alright, we are on unsigned 32 to char8. So unsigned 32. So we're just operating in unsigned space. We don't have to worry about sign extension. And we have a 32, which will be L to RDI, which would be EDI. Or no, it'd be RDI in the memory reference, but here would be EAX. And then we're going to send B, EAX would be AL, into RSI. Let's try that. E. Let's see if that worked. E is unsigned 32 to unsigned char8. So move L, RDI, EAX, move AL to RSI. Yeah, it works. Okay, last one is a char to a short. Char 8 to a short 16. I think both of these might be signed. So we say, hey, move with sign extension, move S, a byte to a, is it a long? Yeah, I think it's a long. Because word long, byte, word long. So this would be word. Actually, this should be byte. Byte to a word. And we're going to sign extend it into EAX, which will be what? AX. So we're saying, hey, take this byte, sign extend it to 16 bits, and assign it into the 2 loader bytes of EAX. So the E part of the AX will still have garbage data in it. But that's fine because we're then going to just move a long, because it goes word, no, this is going to move word, byte, word, long, quad word. Okay, so we're going to move word from AX into RSI. Pretty sure that'll work. Let's double check. So you got move SBW, yep. RDI AX, yep. And then move WAX to RSI, yep. Okay, got all those. It's a nice little exercise. Now we got 3.5. Okay, we got more here. 3.4. Let's do 3.5. Let's go to the next page here. Okay. You're given the following information. A function with prototype void decode 1 takes in 3 long pointers, XP, YP, and ZP. It's compiled into assembly code yielding the following. Void decode. Parameters XP, YP, and ZP are stored in registers RDI, RSI, and RDX respectively. Write C code for decode 1 that will have an effect equivalent to the assembly code shown. Okay, let's try to decode what this assembly code means. Boom, 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 C. Then here, what's going to be a decode function. It's going to, we already have the prototype. Void decode takes in long star XP, long star YP, long star ZP. It's going to return at some point some value. So this moves all of those registers into other registers, which is R8, RCX, and RAX, and then we move those. So RDI is going into RSI, where RSI is pointed to. RSI is a second argument. So it's going to be pointer to YP is equal to dereference XP. Because our DI is getting dereferenced and assigned into 8. 8 is then being assigned into the L value of dereferencing RSI, which is YP. And then same thing, RSI. These values already got saved out though. So these are temporary values. Temp A, we'll say this is going to be a long temp A, CX and RAX, RCX and RAX. If we go back here, RCX is the fourth argument. which doesn't exist, and RAX is of course the return value, which is a bit strange. So XPYP, and then this is going to be return temp C. And in here, we're going to say, hey, temp A is equal to pointer RSI, which is YP. Temp B, which is the YP, is getting assigned into our DX, which is ZP. And then temp C, which is RDX into RAX, which is ZP, is going to RDI, which is XP. I think that's correct. Let's check. Boop, 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 boop. Oh, but it's a void, so nothing gets returned. So we just do that. Forgot that was a void. The ret extraction just returns us back, but just because RAX was set, which is typically the return value, just means that the caller won't use it as a return value. Okay. All right. Pushing and popping stack data. The final two data movement operations are used to push data onto and pop data from the program stack. What time is it? So we've been going for 2 hours and 30 minutes. I have some house chores to do. I need to eat lunch. I need to do some cardio. So I'm going to take a break here. I'm going to try to get all that done as quickly as possible because I want to get back to this chapter. This is really interesting stuff for me. So I'm eager to make some progress on this. Cool. So I'm going to go ahead and take a break here. I'll try to be back within an hour, but considering cardio is going to be 30 minutes and my lunch is going to be at least 30 minutes, that might be cutting it too close, but I'll try.